Okay, good morning. So far we gave some overview about array processing, and we talked about beamforming techniques as an overview. And then we continued with single channel signal enhancement. We talked about the model. We worked about different filtering methods in the time domain. Then we moved to we continue with the frequency domain. Gain, which is also filters. And then we presented three methods like this, the Wiener, which are just examples. Of course, you can work with other examples, the Wiener, the trade-off. We saw also that we can also use a parametric Wiener gain. We talked about these theta and so on. So these are just examples, and to get understanding and also the equivalence or a comparison between time domain filtering and frequency domain filtering. But in practice, of course, we don't work on long signals. We work in the short time Fourier transform domain. So the extension is we have different methods or different ways to move from the frequency domain to the STFT domain. The simplest method is to work with similar gains that we worked in the frequency domain, but apply them in the short time Fourier transform domain. What does it mean? That we take long signal, we use windows, and the length of the windows, we need to choose it in a good way. So it's not too short, it's not too long. Sometimes it's possible to combine different windows and make the enhancement using multiple windows. Sometimes it's possible to choose long windows for low frequencies to get higher resolution in the low frequency, and short windows in the high frequencies, because high frequencies we need less frequency resolution, we need more time resolution because they change more quickly than low frequencies. So that also makes sense, so we can combine. But here, just to give you intuition and understanding, we will work with constant length windows for the short time Fourier transform domain. Okay? So what we do here, we start with a time domain signal. You see these are the vectors, just like we did in the time domain. And we take a length, a certain length. Suppose that we use a length of L of the signal. So we took L samples of the measurements. And then using DFT, discrete Fourier transform, and there are fast algorithms to do that, we move to the Fourier transform. So we can apply DFT to each windowed measurement or window of length L. How do we do that? We have to use windows. If we don't use windows as just rectangular windows, there are some problems and some artifacts. So it's not good to use rectangular windows. Also, when you use the short time Fourier transform, it's important that the analysis window and the synthesis window, which means for the forward short time Fourier transform and the inverse short time Fourier transform, they satisfy some relations. And these relations enable perfect reconstruction of signals. So if you don't process anything, you just do short time Fourier transform and then the inverse transform, you want to get the same signal, just like you start with. So this is called perfect reconstruction. And this we can formulate mathematically this requirement by a certain relations between the analysis window and the synthesis window, as we will see shortly. Okay, so how do we do it? Suppose that we choose here an analysis window of length L. analysis window, common analysis window, Hamming window, and similar windows. So you have selections of windows. And then once you use analysis window, you will have to choose also a window for the inverse short-term Fourier transform based on this window. Okay? And we will discuss how to compute the synthesis window. Here, this is the matrix of the discrete Fourier transform, which we know. So what we do here, we take the vector of measurements of length L. We multiply each sample in this vector L with the sample of the window. Okay? So we can write it as diagonal matrix of G that is multiplied with Y. Okay? So we have here only L multiplications. This is the windowed measurement of length L. And then we multiply it with the matrix of the discrete Fourier transform, this matrix, which is L by L. And we get a vector of length L that contains the frequency beams for this time window. And then we can move this window of Y. How much do we change? How much we need to move? How much? Maybe half. Yes, so it should be less than L. So the jumps that we use for the window, so if we use a window of measurements of L samples, then we will move to the next window. Generally, we can move by one sample, or we can move by more, but it should be less than L. Okay? The question is why? I will ask you think about it, and I will answer it soon. And what is the effect of the overlap? Why do we need overlap? This is also a question that think about it. Why do we need overlap between the windows of the short-time Fourier transform? Anyway, in practice, you don't multiply with this matrix, of course. Okay? Because if you just multiply, the number of multiplication is large. There are fast Fourier transform algorithms that equivalent to multiplying with the matrix W because of this structure of W. So you don't directly multiply it with this matrix. There are algorithms to do it. Instead of L squared, order of L squared computations, you do it L log 2L computations. So they are more efficient. Okay? We know how to multiply efficiently with the matrix W. And this is a vector that contains the frequencies. So the length of this vector is L, which contains the frequency. And we do it here. What is the index T? Generally, index T here, it doesn't have to be the time. It can be the index of the window. So if we jump with windows, this will be the index of the window. Okay? I will write it more specifically in a minute. Okay? So instead of using here T, so we can have an index R for the window. And this is the jump, how much we jump, how many samples we jump from window to the next window. Okay? So if we have a signal, yt, okay, so this is t, time axis. So this is the window. And then let's say that we jump R samples. And the index, so the index of the window will be R, okay? So we can say, okay, it doesn't have to be causal now, even though that we mark it here, but the index here will be R equals to 1, okay? So it will be R equals to 1. Here, for this window, R will be equals to 2, and so on. So what we get, if we started with samples of yt, we have samples like this, samples, okay, as a function of t. Okay, t equals to 1, and so on, 2, 3, and so on. For the short-time Fourier transform, we have it as a function of r, and it can be k, for example, if you like. So it will go like that. It will go as a function of r. Maybe I will multiply it so you see the equivalence in the time. But this r is constant. It's just the jump that we do. This is k. So k goes from either, let's say, from 0, 1, 2, and so on, until L minus 1. And R is 0, 1, 2, and so on, whatever you like. So if we jump, it will be like this. So this is 0, this is R, 2R, 3R, and so on. 4R. And for each point on the grid, so you have a measurement. It's like samples, like here. Okay, so you have a grid like this. Okay, all this grid, and so on. So you have a grid, but for each window, it's a vector. Okay, this is the short time Fourier transform, and of course, the values are complex numbers. So we see it like here in a block form. So if we have a vector of x, of length L, vector of noise of length L, we have the summation. Then we multiply with the window. Multiplication with the window is similar to multiplication with the diagonal matrix. That the diagonal are the window values, the window samples, coefficients. Then we do the Fourier transform for that windowed vector. And we get the frequencies for the window for t, and then we downsample. So actually, we don't compute it for every t. We just compute it for indices r. So the jumps. Okay, and as I said, that r can be 1, which is okay. And it has to be smaller than L. And if we choose a certain window G, for the analysis, for the short-time Fourier transform, we will need to compute synthesis window, which we will talk about the inverse short-time Fourier transform. And the synthesis window depends on G and R and L, actually. Okay, so all these parameters determine the synthesis window. But once we do it, once we work in the Fourier transform, in the short-term Fourier transform STFT domain, we can write this as the summation, okay? Because we have linear relations of the STFT. So we have for each sample, each measurement, each sample here, complex number, it's summation of the complex number of the STFT of the clean signal and the STFT of the noise. And then we can compute the variance of the measurement It contains the variance of x and the variance of v. So you see the equivalence between Fourier transform domain and the STFT domain. So what we can do is to apply a gain, scalar complex gain, to each pixel here, to each value here. Okay, so this is the model in the STFT domain, and we apply a scalar complex gain to each measurement here, noisy measurement here. And we apply the gain. So if the signals, the desired signal and the noise signal are stationary, so this gain, it doesn't need to depend on R. Okay? So it doesn't depend on the time axis. It depends only on the frequency. So here the gain can depend only on K if the signals are stationary. But generally, signals are not stationary. So the gain should be computed or adjusted also in time. So it depends on the time index, R, and the frequency index, K. Okay? And after we find this estimate of the clean signal for each time frequency bin, we need to do the inverse STFT. How do we do the inverse STFT on this? Okay? But before we continue, think about in time. So when you work in time, you work with the filters. So it can be causal filters. In the STFT, there is some latency. So even when we work on window, okay, so in order to process this window, we need this window, and so on, and then this window, and so on. When we do the inverse, there is overlap. So there is some latency between the output and the input, which you need to take that into account. Okay? So when you think about real-time processing, you need to think about how much latency do you have, even if the processing is immediate or it takes time. So, but this is acceptable. So there is some relation between the latency, the output from the input, and which depends on L and R. So sometimes if you want to reduce the latency, you need to use shorter windows, and also it depends on R. Okay, so you need to take that into account. Now, if we write the time frequency bin of the estimate of the signal and the gain, so these gains, very similar what we did in the Fourier transform domain, we can take the same gains. The problem is that the information that is used, so sometimes in the frequency domain we can get the information. In the STFT domain, for non-stationary signals, it's quite challenging, as we will see even with the Wiener filter. Okay? But the expressions for the gain will be similar. So whatever we used in the frequency domain and more, even more expressions, more criteria or other filters, we can use in the STFT domain. I will give you an example, a practical example of speech enhancement, non-stationary signal, and then you will see the challenges of working in the STFT domain with non-stationary signals. How do we do the inverse Fourier transform? Okay, so it looks like that. We take this vector. Suppose that we have this matrix in the time frequency domain for the enhanced signal, for Z. Okay? So we take each vector here, each vector, we apply the inverse Fourier transform for this vector. You see? You take this vector, you apply the inverse Fourier transform, which is like multiplication with the W conjugate transpose. Okay, this is the inverse Fourier transform matrix. And of course, I remind you, we don't actually multiply with this matrix. We have fast algorithms to do that for the inverse Fourier transform. So we apply the inverse Fourier transform, and then again, we multiply with a certain window. The window is G tilde. So this is the synthesis window, G tilde, of length L. And then we get samples of Z, okay? See, this is capital Z, which is in the time frequency domain. This is small z. This is a vector of time samples of the vector Z. We get a vector here, and a vector here, and a vector here. And then we do overlap and add. Okay? So what we do, we take ZT, the samples of Z, are overlaps. And this is an indicator just to show what we do with the vector here. So actually what we did, we take vector of signals, and then vector of signals. We move it by our samples, and then we move it. We move it again with our samples and so on. And then each sample, T, is obtained by summation of these windowed vectors. Okay? So there is relation between G tilde and G and G. This is the analysis window, and this is the synthesis window. Okay? Here, like this. So this is the synthesis window. This is how it looks. Block diagram of the inverse STFT. We multiply with the inverse Fourier transform. We multiply with the window, overlap, add. Sometimes people who are not familiar with STFT, they choose analysis window. They don't do window, which is equivalent as if we choose G like this. So sometimes people who are not familiar with STFT, they just take samples from 0 to L minus 1, so they take rectangular window, which is equivalent. So they don't multiply with any window. And also in the inverse Fourier, inverse STFT, they take the same G tilde, like this, rectangular window. Actually, this is not perfect reconstruction. It creates some problems, so on. So this is not a good choice. And in addition, that the inverse Fourier STFT does not reconstruct the original signal, it creates also artifacts. So let's talk about the relations between the analysis and synthesis window. If we take, you see, suppose that we take any signal like this. We multiply it with a window and apply the Fourier transform. So this is the STFT of the signal. Now suppose that we want to reconstruct the original time domain signal from the STFT signal. So we apply the inverse DFT, we multiply with synthesis window, and this is the overlap and add. Okay, we take the signals, we move it by our samples, and this is the overlap and add. So we can write the relation between the time domain signal here and the time domain blocks, vectors of length L, like this. So in order to have this equation correct for any signal x, this is called the perfect reconstruction uh, uh, condition. So if we want to have perfect reconstruction, we need that this will be satisfied for any time signal x, which means that this, you see here, so this relation should be satisfied. From here, we can come here. By the way, anybody that wants to go through the mathematics, just do it and prove any step in the derivation. But I want you to understand it, so I don't go about all details, but it's straightforward if you do it yourself. Okay? So this is, if we require that this is satisfied for any time signals x, so this should be satisfied. This is called the exact reconstruction condition. So you see, it depends on what we chose for the analysis window, the G, what is L, and L, because L comes from here, the G. The window G, its length is L. Okay? And then we have here another parameter, R, is how much we jump or we move from one window to the next window. So all these determine what will be the synthesis window. So what I say that you here, suppose that you choose an analysis window of length L, and you choose step size R, then the solution to that, there are infinite number of solutions to find G tilde synthesis windows that satisfy the exact reconstruction condition. So there are many solutions. But usually we choose the solution with the minimum norm. Okay? But you need to know that this is just one solution out of infinite number of solutions so that you can choose, but it makes sense to choose minimum norm because it's a smooth with and a minimum norm, which means that you don't have much variation in the synthesis signal. Okay, so how do we find G tilde from this equation, the minimum norm solution? We can write it in a vector form like this. Okay, we can write it like this. This is the condition, the perfect reconstruction condition like here. And minimum norm solution for that, it's simply like this. This is the minimum form solution to this vector form perfect reconstruction condition. So the minimum norm solution, like here, is simply, we can write it like this, sample by sample. Okay, so it means that if we choose a Hamming window, many times people don't choose rectangular windows for the analysis and synthesis because they understand that it's not perfect reconstruction. But what they do, they choose the same window, like, for example, Hamming window for the analysis and synthesis. This is also incorrect. Okay? Because you need to choose a window, synthesis window, that satisfies this condition. By the way, if two windows satisfy the perfect reconstruction condition, they are called biorthogonal windows. Okay, let's move on. Okay, so the input SNR for each sample is this ratio, is the variance of X in that sample divided by the variance of the noise in that sample. And then we can get optimal gain just like we saw for the Fourier transform. We can apply that. We can also compute the wideband input SNR and wideband output SNR, like this, which is summation over the time and frequency indices, all the time frequency bins that we want to apply and measure that. And we can also compute the broadband noise reduction factor and broadband desired signal reduction factor. We just take the summation instead of what we did for the Fourier transform. We took summation only for the frequency, or we wrote it as integral, but it actually can be thought as summation. Here we take summation over the time indices of the windows and also the frequency indices. So we take summation over the time frequency bins of the STFT. We can also compute the broadband MSC as summation over the time and frequency of the MSC for each time frequency bin. Let's see an example. Okay? So in this example, we would like to work with a practical signal, like a speech signal, that is sampled at 16 kilohertz. Okay? Afterwards, I want you to repeat this example and do it on your own voice. Okay? And play with this, because this is a very nice example to work with and try it on your own. Okay? So suppose that I have a speech signal and it's contaminated with Watt Gaussian noise with a certain variance. Okay? So the input SNR, and suppose that we work, we apply the STFT, short time Fourier transform, with a certain, with Hamming windows of length 512 samples. 512 samples for 16 kilohertz, it means like the length is 32 milliseconds. 32 milliseconds makes sense for speech because it's not too short interval or window and not too long. So we can assume that within this short window of 32 milliseconds, the signal X is almost stationary, which is not completely true, of course, but it can be approximated as stationary within that window. So if we want to apply the Wiener filter, so the Wiener filter will generate, okay, some distortion. So of course, if the noise is large, if the input SNR is low, we need to reduce more noise. And then what will happen that the distortion, the signal, the enhanced signal will sound more distorted compared to the original signal. But see what happens here. Okay, so this is the Wiener, which is, we know, just like in the frequency domain, we derived it, so we take the same expression. So the input SNR divided by 1 plus input SNR for each time frequency bin. And I mentioned here that the input SNR, it's very difficult to know for non-stationary signals. Okay? So first, what you can do at home, you can take the code and try to put input SNR for time frequency bin R and K. If I take something like instantaneous input SNR, suppose that I take in the STFT domain X, R, K, R. Okay. R, K. So I take the time frequency domain of the clean signal, and I take its magnitude squared without expectation, because I don't have it. It's a realization of the signal. And I take here V, R, K. Okay, something like that. magnitude squared. Suppose that this is like instantaneous input SNR for a specific time frequency bin in the STFT domain. This is like ideal. Something, suppose that I knew to obtain this ratio, and I put it in the expression of the Wiener filter, it will generate excellent performance. What do you think? Even if I take something like that, the enhanced signal will be distorted compared to the original signal or not? Will I get some distortion or not? Yes or no? 50%, you are right. Even without just say, if you don't say anything, it's incorrect. But if you try yes or no, then you have 50% correction. 50% correct. So it's better to say something, okay? It's better to say a wrong answer because with 50% success than not do anything. Okay, so if you want to start your own company, so you can say, I will not be able to do that, and I promise you, if you don't do that, you fail. But if you do that, you have a certain percentage or certain probability to succeed. So it's better to try. And if you fail, you try again. If you fail, you try again, okay? So don't be afraid to try. It's not a problem to fail. And it's not a problem to say something which is wrong because it makes you progress, okay? So what do you think? If I use this ideal input SNR, I use it for the Wiener gain, and I apply it to the original signal. Will the enhanced signal will be distorted or not? Yes or no? Yes, of course. It will distort because Wiener filter distorted. If I want that the enhanced signal will not be distorted at all, what do I do? What? Again, it's hard to hear if you speak louder. What? Yeah, but I don't want you to say just NVIDIA. I want you to say, because it's a simple, much simpler answer you can give me. Okay? Think about, suppose that I know which samples here, which time frequency bins contain desired signal and which do not contain signal. So I will use a different gain, H. How will it look like? So it can be 1 if X, R, K, okay, is not 0. 0 if X, R, K equals to 0. Do you agree that I can choose a gain like this? So if I multiply Y, each sample of Y, each time frequency bin of Y, I multiply with this gain. And then I do the inverse, STFT. Do I get any distortion of the signal? Of the desired signal? X will be distorted in the output? Yes or no? I hear yes or no? No distortion. Right? No distortion. Because I didn't touch, I didn't change any sample, any time frequency bin that contains the desired signal. No distortion. But think about, by the way, this kind of method, it's called mask. Why? Because it's mask. It's just, I multiply each bin with a mask. So I estimate where the desired signal is present, where is not, and then I have no distortion. Do I get perfect noise reduction? Yes, perfect noise reduction. Let's remind you that we have trade-off between signal distortion and noise reduction. So do you think that Z which is actually H, mask. This is, sometimes we call it a mask. If we multiply it with Y, and then we do the inverse STFT, do you think we will perfectly reconstruct the original signal without any noise? No. Why not? Why not? Okay, so there is still noise. So we keep the noise in all time frequency bands where the signal is present. But we put to zero all the noise components which are only noise. So remember, we talked about signal plus noise subspace and noise subspace. So noise subspace in this representation is all the time frequency bands that contain only noise. So we'll null them. We put them to zero. And all the time frequency bands that contain signal plus noise, we keep them without touching them. So we keep the noise in those time frequency bands. Okay? So I want you to try this with the Wiener. I want you to try this perfect mask. Okay, so this is a perfect mask. But actually, and then you can compare. Okay? When you compare, try to listen to the enhanced signal. Try to listen if it's distorted or not. And don't compare for high SNR. If the SNR is high, then H becomes closer to 1. Okay, so try to compare when the signal to noise ratio is low, 0 dB. Even lower. Try even lower, minus 5 dB. It's nice, okay? But think about this mask is like ideal mask because it shows like I know the clean signal. By the way, this mask is even not something that we try to achieve, okay? Because if there is a very, very small contribution, very small value here, we don't want to keep it. Okay, so usually it's not based on X. It's based on how much X is larger than V by a certain threshold. So this is another way for ideal mask to put it like this. So it's either 1 or 0. By the way, it doesn't have to be binary. We can take something like Wiener. But also, you know, I will put even something like the Wiener, okay? So I will use this input. Input SNR divided by 1 plus input SNR. Okay. For each time from here, we can use it here. If input SNR is larger than a certain threshold, which is epsilon. And 0 if input SNR, the instantaneous, this is the ideal, is smaller than epsilon. And you can choose epsilon according to what? If I increase epsilon, what happens? If I increase epsilon, do I increase distortion or reduce distortion? Increase? Decrease distortion? Actually increase distortion. Let's think why. If I increase epsilon, it means that I keep or process, or here, I keep time frequency beams such that the value of x is sufficiently high. Here I can put some value. Here I put to null all time frequency beams such that the instantaneous SNR is lower than a certain threshold. It means that I will distort very low, very weak components of X. Weak components compared to the noise. Okay? So if I put to 0, I remove weak components of the original signal, I have some distortion. But the distortion will be low. It will be low because I remove only weak components, not the strong components. If I take epsilon larger and larger, I will reduce more noise, but I will pay for that. The distortion will be higher if epsilon is higher. So you can try this kind of Wiener, ideal Wiener, combined with a mask, with ideal mask. Okay? Why do I call it ideal? Because I assume I have the instantaneous SNR for non-stationary signal. So this is very difficult to achieve, this ratio. But we try to approximate to find it differently. Okay? So let's continue. Any questions so far? Any questions? Okay, good. Actually, it's good if you have questions. If you have no questions, I don't know if everything is clear or not. Okay. Okay. So if you have questions, please ask. Now, okay. In practice, of course, we don't know the input SNR. In practice, we don't know this ratio. This is. So I will give you the MATLAB code to do speech enhancement, and then try different things. Play with it. So this is a very good assignment. Even though I don't write it, I didn't put it on as an assignment. I think it will enable you to understand the challenges in practice for real signals and non-stationary signals. So I encourage you to do that. It's very important. Now, because I don't know that input SNR, what can I do? I will try to estimate the variance of V. Okay? So the variance of V, I will take it during windows that don't contain the original signal. So for speech, you see when people speak, there are always some pauses of speech, either in the time or in the time frequency beam. So sometimes I know when speech is active, during which windows there is speech or not. There is something like that. These algorithms, do you know how we call these algorithms? What? Voice activity, exactly, voice activity detection. In short, VAD. Voice activity detection. There are efficient algorithms for voice activity detection, which are very important. And actually, it enables us to do some things, you see. So if we average the measurements, the noisy measurement in the STFT domain recursive averaging, which is very efficient to do, we can obtain the variance of V, because during these windows, we don't have the desired signal. We assume the desired signal is 0, or in practice, it's below a certain threshold. It's weak enough. And if there is a present desired signal present in the window, we don't change the variance. So we stop the recursive averaging. This is a good way to estimate the variance of the noise. I remind you that input SNR, what is the input SNR? Instantaneous input SNR. In practice, let's delete this. So I remind you that, that in practice, the input SNR is phi x divided by phi v. So we can put here estimates. So phi v, if the noise is stationary, this is a good way to estimate the noise. If you're interested how to estimate non-stationary noise, I can give you a nice paper about it. If you're interested to know more, I can give you, you can read a paper. It's not complicated. But I don't want to go beyond too much outside the scope of this course. Okay, so if the noise is stationary or changing slowly, not too fast, then this is a good way, recursive averaging during inactivity of the speech. It's a nice way to estimate the variance of the noise, the denominator. The main problem with speech is to estimate the numerator, the variance of the desired signal, because it changes very quickly. Okay, so how do we do that? So a simple way to do that is to take the variance of y and to remove or subtract the variance of v. Okay, I remind you that the variance of y equals to the variance of x plus variance of v. Because y, this is in the STFT domain, equals to x plus v, and x and v do not correlate with each other, aren't correlated. So this implies this. But this is true for the true variance, not for their estimates. That's why if we try to estimate phi x hat using phi y hat, an estimate of variance of y minus variance of v, we cannot do that because maybe it's negative. These are estimates, so it's not satisfied for the estimate. So we put here max between this and 0 because we want it to be larger than 0. And actually, for speech, we can put here a factor, beta, where beta is larger than 1. And the effect of beta, what will happen if we increase beta? It means that we put, remember mu for the trade-off? Remember mu? Good. So if this is similar to mu. So we put more weight to the variance of the noise. So it's just like if I put mu, if I put here a square root of mu, you remember that this is similar to the trade-off, okay? But instead of square root, I call it beta. So but it's the same role, the same feature, like to put here square root of mu. And if I increase beta, okay, what will happen? I give more weight to the noise. It's just like I increase the subtraction of the noise. And then what will happen? If I use larger beta, what will happen? I reduce more noise or less noise? More noise. Very good. I reduce, if I increase beta, I subtract more noise. What will happen with the desired signal? More distorted. This is the trade-off. So I can use something like that here, and I can change beta. Increase beta, more noise reduction, more distortion. Let's see. This is clean signal. This is the spectrogram. If you're not familiar with spectrogram, actually it's the magnitude squared of the STFT. So we call it just like the matrix I showed before. It looks like that. So first, take a speech signal. You can record yourself using the laptop. You can speak, recording, and then compute the magnitude squared of the STFT on a log scale. So this is in dB. The color or the shade goes like it's after we convert it to dB in decibel. Okay. You have the code, MATLAB code, because this figure comes from the book also. So you have the MATLAB code. You can play with it. This is the clean signal. You see, no noise. Very clean. This is the clean signal in the time domain. By the way, sometimes if you want to put a figure of speech in a paper that you write, conference paper or journal paper, this is a nice way to achieve it. So you can use my code to generate something like that, okay, to see how much noise and so on. So it's a nice way. And you can do it also with color, if you like. Also the spectrogram. Here we see the gain in SNR, the MSC, the noise reduction factor, and the desired signal reduction factor. For a noisy signal, let's see what is the noisy signal. How much noise? I added some noise. Okay. Maybe I have it here. So I have some noise. Oh, okay. So it's as a function of the input SNR. So I can take the clean signal. I can add Y stationary noise such that the input SNR will be certain value. This is the broadband input SNR. Okay, so the blue line is with beta equals to 1. This is red, beta equals to 2. And then 3 and 4. So you see for a given input SNR, as we increase beta, what will happen? More noise reduction. The noise reduction factor increases, which means that we suppress more noise. And the output SNR, the gain in SNR, will be also higher because we suppress more noise. Why, when we suppress more noise, the output SNR increases? You know why? Remember the maximum SNR filter? We talked in the time domain. Maximum SNR filter. When we suppress more noise, okay? When we suppress, we don't suppress noise in high SNR components. Where do we suppress the noise? In low SNR components, which means that we come closer and closer. The more components that we remove, we keep only the high SNR components until maybe we keep only the last component with the highest SNR. And then it becomes like the maximum SNR filter. Okay? That's why. So when we suppress more noise, the output SNR increases. If you did something wrong and you suppress more noise in the high SNR component, you remove the high SNR component, you also remove more noise. But this is not a smart thing to do, because then you increase the distortion and maybe the output SNR will not increase. Okay? So I connect you with things that we discussed. All things are connected. You see? When you understand these things. Okay, so because that we suppress noise in the lower lower SNR components, we necessarily, when we increase the noise reduction factor, we increase also the output SNR. But it comes at a cost of increasing the distortion. The distortion in weak speech components, not the strong speech components. Because we want, first, when we reduce noise, we want to reduce or suppress only the lowest in our components. So we have less distortion. But still we have distortion. So you see, when we increase the noise reduction factor, we also increase the desired signal reduction factor. So we have more distortion. We pay for that, okay? So when we have more noise reduction, more signal distortion. And the MSE, mean squared error, decreases. Okay? So beta and mu play here similar roles, which is nice to see. How the realization, so if we take a realization of noisy signal, so here the signal to noise ratio with this realization, I don't remember, I don't see that it's written, but probably realization, so probably it's in the code. I don't remember what is the signal to noise ratio here. Okay, but we have a certain signal to noise ratio here. And then this is the enhanced signal when beta equals to 1. So you see, when beta equals to 1, we still have many noise components where we don't have speech. Here, beta equals to 2. Here, beta equals to 3. So when we increase beta, we remove more noise. But you see, we also suppress or remove weak speech components. So we have more distortion. So what I want you to do is to take, read the code, the MATLAB code for this example, play with it. Play with it, change beta, listen to the reconstructed signal, play with ideal mask like this, play with ideal Wiener filter like this, which is combined with ideal mask and some ideal mask with ideal ratio, and compare it to the non-ideal, something like that with beta. By the way, phi y, what do I do? How do I estimate phi y? Two ways. Either I can take phi y I can take it as magnitude squared. I can do that because these are the noisy measurements. So this is one way. But then try it. But in the code I didn't do this because there are variations because of the noise. So y is fluctuating. So instead of something like that, I took this and I took some averaging of neighboring time frequency beams. So when I compute for this time frequency beam, I take some window, like image smoothing. So this is the image, these are the samples. So I take some smoothing around it with a certain window. Let me see. Maybe it's before the sample. Here. You see, it's obtained two-dimensional convolution between the magnitude squared and a smoothing window. So I can take. So if I do more smoothing, then I distort the desired signal more. If I do less smoothing, then I have fluctuations. So this is also a trade-off. So you see in practice, you have many trade-offs, many parameters. So you try something, you hear, you listen, you try to improve it. So play with it. And if you're interested to read a paper on speech enhancement, which you have some background on this, I can give you, I can recommend you. I can give you a paper. Just let me know. I will share it, okay, and then the WhatsApp group, okay? I can send it to you. For those who are interested, who have time. Any question? How do I estimate what? Which one? This? V? This? So this is what I said, that suppose that I have a voice activity detector here. You see? So suppose that I know when X is present and when it's not present. Voice activity detector, which is not easy, but there are some algorithms for voice activity detection. I can recursively estimate, average the noisy samples during inactivity of speech, and during activity of speech, I don't do any recursive averaging. So you need to work on that also. Because for speech, there are intervals where speech is not present, and if you have a voice activity detector, you can recursively estimate here. But if you have some applications that you know that the noise is stationary, and you know durations of periods that you have no signal, you see also with radar or something else. You know when there is a signal, when there is no signal, because you send the signal. But you need to know if the noise is stationary, because you calibrate or you make measurements during inactivity of the signal, so you assume that the variance remains the same when there is a signal, because I keep it. Yes, but the noise, maybe you have other interferences which are non-stationary. But if it's stationary, it's okay. So you estimate during inactivity. Mm-hmm. Yes. But if the variance of the noise it does not change, and you know that you didn't submit a signal, so you know some intervals where you don't have the desired signal, so you can get an estimate of the variance, which is okay, right? But I agree with you that there, in practice, you need to think what you do. You need to know what is the definition, when the signal, the noise, what is the type of noise, if it's stationary or not, if I can assume that the variance remain the same, how do I estimate it? I'll give you an example. So I have a good example. Suppose that there is a television somewhere here. And on the television it plays some speech and music and so on. And then I speak at the same time. So the speech, the desired signal, is non-stationary. But the noise from the television is also non-stationary. How do I suppress it? Okay? So it's more challenging. So also I can say, suppose that 5 people speak at the same time. 5 people speak at the same time, and I have a measurement, single channel measurement of 5 people. If I listen to it, it will be very difficult to listen to each one individually and to understand it. I need to concentrate, and maybe concentrate on the voice of one, and then another one, and then another. It will be, I can maybe, I can play something. Okay, I have a good example. I will play something, maybe after the break. I will look for a YouTube demonstration of something very nice. People speak at the same time. You see, it's difficult. And then I want to do source separation. Sometimes we call signal enhancement when we have background noise and it's some sort of stationary. But source separation, two speech at the same time. Two speakers speak at the same time, it's very difficult to listen. Not to mention if there are 5 speakers at the same time. Is it possible to separate, to extract just one of them? Any one of them. And then you can listen separately to each one of them. Very challenging. Is it possible? People are working on that. There are some solutions. Very nice. Very nice demo. I will show a demo after the break. Any other question? Because I don't want to waste time when I look for it. So I will do it during the break. Any other question? Okay. So until here, we worked with single channel signal enhancement. Now we want to move to multi-channel signal enhancement. How are we concerning the time? So we have, so it's 10:15. I'll give you like 5-10 minutes break. And then we start with multi-channel.